Good day, everyone. So let's get busy with operational amplifiers. And to begin, an amplifier is a device capable of increasing or boosting the power in low-level signals. So we have op-amp, for short, for operational amplifiers. And schematically, we could represent the operational amplifier with some black box, say designated with some parameter A, having the input terminal voltage and the output VR terminal voltage. And here we see that the output is a scaled version of the input voltage. Hence, the output is seen as the amplified version of the input voltage. So this takes care of the amplification phase, amplification process of the operational amplifier. And then we have another term here, which is operational. And this derives its meaning from its application in analog computer circuits. Further to the diverse operations of the direct current coupled amplifiers in performing operations such as addition, subtraction, differentiation, integration, and many more. So hence, the operational amplifier is an integrated circuit. As opposed to the previously described or discussed discrete circuit elements, the likes of resistors, capacitors, sources, and so on. So with this, it's worth mentioning here that the operational amplifier, or better still, the amplifier itself, could be modeled using the Thevenin equivalent circuit of a practical voltage source. And there we'll get a voltage source connected in series with some resistor. This is the voltage source connected in series. Some input resistor. You see, this is the source, and it's going to be coupled with the load. We have the load resistor at this point, RL, for which the voltage across the load is designated as VM. Now, you'll observe that at this terminal, we have the input voltage, the input to the amplifier. So here, this is the source, this is source, and here, this is the load. And so we have the amplifier in between, okay, which couples the source with the load. Now, at the input to the amplifier, we have the input voltage, okay? And since the amplifier is meant to boost the signal level, as already established, where V0 is the same as A V in, then the load RL will see an amplified version of the input voltage, which may be modeled using an independent voltage source. So at this point, plus minus AVN. So in other words, this is some dependent voltage source depending on this input voltage, but scaled by some parameter A. Now, since the source itself looks like a Thevenin equivalent circuit where we have a voltage source connected in series with the resistance RS, then the resistance at the output will be connected in series with the amplified voltage, such that we have something like this, which will now be the output resistance. Okay. Now, the source itself will therefore see the input resistance of the amplifier, such that we have the input resistance of the amplifier here. And this is R in. So this model here therefore represents the black box. Okay, this is the amplifier. Now, summarily, you'll observe, summarily, you'll observe that the source, that is the source, V sub S, sees an equivalent resistance. Sees an equivalent resistance, R in, looking to the right, while the load sees an equivalent source, that is AV in, AV sub in, looking to the left. And by way of observation of this amplifier model, you'll observe that the amplifier model has some specific parameters. Now, let's change the color. So from the amplifier model, we have that in this model, we have the input resistance, R in. Then we have the output resistance, RR. We also have the input voltage, V in, the input voltage, and then we have the gain, A, which is also referred to as the open loop voltage gain. That is A, right? Perfect. So if we go back to this model to analyze it, then we'll be able to identify some specific parameters in relation to the ideal amplifier. Good. Now, if we apply the voltage divider rule, so let's say by voltage divider rule, let's say at the source, at this point of the circuit, we observe that Vin is the same as Rin divided by Rs plus Rin is so less. And at the load, if we apply voltage divider rule, then V sub L, the load voltage, will be the same as RL divided by RR, the output resistance plus the load resistance times the voltage, the amplified voltage, AVE. Now, if we consider an ideal system, so let's put that down. If we consider an ideal system, then at the source, Vs will be the same as Vn. That is, the source voltage will be the same as the input voltage. And for this to hold true, for this ideal scenario to hold, you'll observe that Rin will have to extend to infinity. This will have to extend to infinity, and this extends to infinity. Then if that happens, then the source resistance will become negligible, such that Rin extends to infinity, such that Rs is far, far less than 0. Then the source voltage, then this will reduce to a unit value. Then the source voltage will be equivalent to the input voltage should the input resistance extend to some infinite value. And at the load, for the load voltage to be the same as the amplified input voltage, then R out will have to reduce to 0, because if, now for this to hold true, then the output resistance has to should reduce to 0. And if the output resistance reduces to 0, then this reduces to a unit value. So at the load, R out has to be 0. So these parameters will become very handy when we begin to play with different configurations of operational amplifiers. Now, if this is taken, let us quickly consider the configurations, or better still, the schematics, before talking about the inverting and non-inverting configurations. Let us talk about the schematic representation of an operational amplifier. So the operational amplifier is usually designated in this manner, where we have the power supply, and in most tests they are excluded, okay, and the power supply terminals are very necessary in the actual device because the amplified power comes from some external source, okay. So and then we have the output. This is the output. This is positive power supply. This is negative power supply. Then we have the terminal connected to the positive terminal is usually referred to as the non-inverting terminal, while the negative terminal is usually referred to as the inverting terminal. And the second model of the operational amplifier, just like we already discussed, therefore looks something like this, where we have the input Rin, which is the input resistance, and then the amplified voltage. Here we have, this is plus minus, the input voltage, Vn, positive, negative. This is the non-inverting terminal V sub P, and this is the inverting terminal V sub N. And then we have the amplified version. This one, oh my goodness. Okay. So drop this here, connected to the input resistance in series, the output resistance rather, and then this goes straight to the output. And then I have all of these in this huge triangle. Okay. Yeah, this is the output voltage, while this terminal is connected to ground. Now you will notice that the amplifier responds only to the difference in the voltage between the two terminals, between the non-inverting and the inverting terminals. Okay, and as such, we begin to talk in terms of node voltages, so point voltages. Now, since the terminal or node voltages are of interest, then technically in analyzing op amps, then the nodal technique will be very useful. Okay. Alongside the Ohm's law and the laws. So we can therefore summarize here that the ideal op amp exhibits the following characteristics. Now, the input resistance is infinite. That is, Rin is equal to infinity, like we already addressed. And this will ensure that no current flows into the amplifier input terminals and the source network is not loaded. So therefore, the current through the non-inverting terminal will be the same as the current through the inverting terminal, and it will be 0. And the second point here is that the output resistance RR is 0, like we already derived. That's RR, the output resistance is 0. And this will ensure that the amplifier performance is not affected by the load. And also, the open loop gain, or better still, the differential voltage gain, which is designated as A, is infinite, as A is equal to infinity. Now, this will also ensure that the performance of the amplifier is entirely dependent on the input and the feedback. Okay? And then, once the input signal Vin is 0, the output signal Vout will equally be 0. That is, Vout is 0 if and only if Vin is also 0. And then since Vin is the same as the difference between the node voltages, which is Vp, which is the positive minus the negative node voltage, and then this then therefore tends to 0. Therefore, Vp is the same as Vn. Okay. And now the bandwidth is equally infinite. W is equal to infinite. Now this will ensure response to DC signals and no phase change with frequency. And also, the negative feedback that is with the negative feedback, this the differential input voltage reduced to 0. Now, before we take things a little step further, let us address some important terminologies. And the first is differential amplifier. Now, this is an amplifier designed to amplify the difference between two signals. Recall that we already have VP, VN is positive, negative. I already established that this is the difference between Vin is the difference between these 2-point on-node voltages. And now we are saying that the amplification process, what we get at the output, V out, is actually a Vin, which is the same as a Vp minus Vn. Okay, so that's why it's called the differential amplifier. So it is an amplifier designed to amplify the difference between two different signals. And for an ideal op-amp, we have V naught to be the same as a Vp minus Vn, where A in this case, like we have mentioned earlier, is a differential or open loop gain. And the second terminology we need to also consider is the differential input signal. Differential input signal. This is designated as V sub D, or better still, V sub in. Okay, V sub in or V sub D as per the word differential. V in. And now V in is the same as V sub D, is the same as V sub P. This is positive with respect to this, which is negative, V sub A. And in some of the standard tests, it could be represented as V super positive sign and V super negative sign. Okay, where V sub P is the same as V super plus sign is the signal at the non-inverting input. Signal at the non-inverting input, y V sub n, the same as V to the power minus here, is the same as the signal at the inverting input. Okay. Then the next point to consider here is the differential gain. Gain, which is the same as A, or it could be A sub D, should we tie it up with the word differential. Okay. And now this is the ratio of the output voltage V naught to the input voltage V in. Okay. When the common mode voltage V sub C is equal to 0, for which the non-inverting voltage is the same as the negative of the inverting voltage. And then we have the common mode input signal, V sub C. And this is the average of the two input signals. Okay, so say this is the average of the two input signals. Here we have V sub C is the same as V sub P plus V sub N divided by 2. And also, we have the common mode gain. Common mode gain. And designate this as A sub C. And this results from the same signal being applied to the two terminal inputs of the op amp. That is where Vp is the same as Vn, such that the two terminals coming in here happen to be probably Vp, Vp, or it could be Vn, Vn, so they are the same, okay? And it is the opposite of the differential gain. So hence, A sub C is the same as V naught divided by V, where V in is equal to 0, such that the non-inverting voltage is the same as the inverting voltage. And recall that for the differential gain, the non-inverting voltage is not the same as the inverting voltage. And then we have the common mode rejection ratio, MRR. Now, the common mode rejection ratio indicates how much better the differential amplifier is at amplifying differential signals than the common mode signals. Okay, so how well is it able to amplify the signal when we have both terminals not being the same, where Vn, where Vp is not the same as Vn, that is Vp is the same as negative Vn, that is for the differential signal. And also when we have the common mode signal where Vp is the same as Vn. Okay, so it is a figure of merit of the differential amplifiers, and it should be high. The value should be high, and therefore we can designate this as V naught to be the same as A sub D V sub in, which is equal to, or better say plus, A sub C V sub C. And this is approximately the same as A sub D V sub E, which is the differential gain, or technically A B E, okay, which we'll be using as our convention most of the time. Okay, now the common mode rejection ratio is the same as the modulus of A divided by A sub C. And in decibel, dB, we have 20 log to base 10, which is A dB minus A sub C dB. And you will note that practical differential amplifiers respond not only to the difference between the input signals, but they also respond to their average value. And hence, the evaluation of the common mode rejection ratio. Okay, with this, we can now delve into the description of the configurations of op-amps. And we do have about two major configurations. That's op-amp configurations, op-amp configurations. So we have two types: inverting op-amp configuration and non-inverting op-amp configuration. So we'll begin with the inverting op-amp. So from the term here, inverting, it means that it produces an output signal that is out of phase relative to the input. Okay? That is, the output voltage changes in the opposite direction as the input voltage. In other words, V in and V out are 180-degree phase shifted. So the negative sign we'll see here will account for this phase shift. So let us look at a simplified circuit model. So here, the source is connected to the inverting terminal and the feedback is connected between the inverting terminal and the output. Okay. While the non-inverting terminal is connected to ground. And the source voltage, so they all have a common ground, and the output voltage also, the output is connected to ground. So here we have the output voltage, here we have the source voltage, then we have R1 here, and the feedback resistance here. So there's a connection. And before we go on, it will be a smart thing to recall the assumptions. Now, let us recall the assumptions for an ideal op-amp. Recall that the input resistance is infinite, that is, can be represented using an open circuit. Then the output resistance is the same as 0. It can be represented with a short circuit. The differential gain is large, extremely large, is infinite. V in is the same as Vp minus Vn, which is the same as 0, such that Vp is the same as Vn. Good. So with these assumptions, we will now be able to present the circuit model of this of the inverting op-amp circuit. Now we have, okay, let's use some other color. So this goes all the way. Now the input resistance is an infinite value, so we'll represent with an open circuit. Then we have the feedback. This is R1, then this is RF. And then the output resistance can be represented with a short circuit. Okay, so it means R in is equal to infinity, then R out is equal to 0, presented with a short circuit. And then we have the amplified version. Here we have positive, negative V in here. Here, this is positive, negative, the source voltage. And this is positive, negative, A, B, E. Then we have this connected to ground. Then the output voltage, which is V out. Yeah, this is equivalent circuit. Okay. Now you recall that we previously established that the node voltage technique will be more appropriate in analyzing the op-amp circuit, likely because we are now dealing with node voltages. This is the non-inverting terminal, which is Vn. So let's use another color for the node voltages now. This is Vp, and then this is Vn. And Vn is the difference voltage between Vp and Vn. And now we have I1 flowing this way. Then we have IF, I sub F flowing this way. And you observe that the entire current that flows into this node flows all the way. So IF will be the same as I1, right? Yeah. Good. Now, if we apply KCL at the negative terminal, okay? Yeah, there's something going on here. So this, oh my goodness. Okay, now the circuit has been shifted upward, and we have the assumptions this way. So if we write KCL at the negative terminal, at the non-inverting terminal, then we'll observe that at this node, at the negative terminal here, I sub 1 flows in and I sub F flows out. So KCL at the negative terminal will give us I sub 1 is the same as I sub F. That is, the current flowing into the node is the same as the current flowing out of the node. And now, at this terminal, we have V sub S, which is positive with respect to the reference node, and therefore, by Ohm's law, I sub 1 be the same, because this is positive, negative here, positive, negative. So that will be V sub S minus V sub N divided by R1, which would be the same as now this node is V naught, which is positive with respect to the reference node. So V sub N minus V naught by Ohm's law, V sub N minus V naught divided by the feedback resistance. Okay, so this will be the same as V sub S minus V sub N, RF, we cross multiply, V sub N minus V naught, R1. So if we collect like terms here, V sub S RF and blah blah, so V sub S RF will be the same as V sub N RF plus V sub N R1 minus V naught R1. And V sub S RF will be the same as V sub N RF plus R1 minus V naught R1. So let's say this is our first equation. Now at the output, at this point of the circuit, since we have a dependent voltage source, we may not be able to characterize the direction of current flow by the source with ease. So hence, we won't be able to analyze this part using the KCL, but we could do this by writing KVL around the loop, okay? And if we, let's try this. Okay. Okay. So KVL around the output. So that is right KVL here. So that will be negative AV in, negative AV in plus, goes all the way, plus V naught as the sum of voltage drops around the loop or mesh is the same as 0. Okay. Now we have that negative A V in is the same as negative V naught. So V naught in this case is the same as AV in. Yeah. So V in, the input voltage, is the same as V naught divided by A. And recall that so part of the assumption for an ideal op amp is that the open loop gain or the difference or the differential gain is infinite. So if that is true, then V in will reduce to 0. And therefore, if V in is the same as 0, then Vp that is V in, which is the difference between this and this. So let's write it. Let's write KVL at this node instead for ease of understanding. So KVL at this node, that is V in, is the same as Vp minus Vn. And we already have V in to be 0, it's equal to 0. So it means that Vp is equal to Vn. Okay. And by way of inspection, the reference voltage here, Vref, is equal to 0. Vref is equal to 0 all the way. The reference voltage is 0 volts. The reference voltage is equal to 0 volt. And the positive terminal is connected to the reference voltage such that V sub P is equal to 0. And therefore, it means that V sub P is equal to V sub N is equal to 0. Okay, so let's make this our second equation. So if we plug in the second equation into our first equation, so if we put 2 into 1, you observe that this parameter will reduce to 0, such that V sub S RF will be equal to negative V naught R1. Okay, and now from this point, we can rearrange. We say V naught divided by the output voltage divided by the source voltage will be the same as the negative of the feedback resistance divided by R1. And this is referred to as the closed loop gain. Okay. For a non-inverting op amp. So here we have been able to establish that the closed loop gain is the same as V naught over V sub S equal to negative RF over R1, where A sub V is referred to as the closed loop gain. And also, you will observe the negative sign, which accounts for the 180-degree phase shift, that is an inversion. Hence the name inverting op amp. So technically, regardless of the infinite open loop gain that we have here, a closed loop gain of some finite value of probably some designated value could be designed by choosing an appropriate value of the feedback resistance and the input resistance, or better still R1, not the input resistance, the source resistance. Okay, so let's consider a simple example. So here's a simple inverting op amp. And we have to evaluate the open loop gain, the output voltage, the source current, and the output current. Now recall that the open loop gain, okay, before we go on, let us recall the relevant assumptions, okay? Now, this is V sub N, this is V sub P, okay? There's the inverting terminal, the non-inverting terminal. Now, V sub S is positive at this terminal relative to the reference voltage, which is 0. And so we have V sub positive X here. And then we have IS flowing in this direction. and then we have IF flowing in this direction. Now, the current that flows into this node flows all the way to the feedback. So through the feedback, so it's the same as IS. Now we have the output current flowing in this direction, and the load current in this direction. So we have the output voltage. So we already know that the open loop gain, or the closed loop gain rather, closed loop gain is the same as the ratio between the output and the source voltage, which is the same as negative RF over R sub S. So let's put it as 1 here based on our notation. Good. And R sub F, the feedback resistance is 200K negative, and the source resistance is 20K, and this will give us negative 10. So the closed loop gain is the same as negative 10. Also, from the closed loop gain formula, we can estimate the output voltage because we have V naught over V sub S. This first, and this next. Excuse me. Same as negative RF. Now we have the source voltage to be 1 volt. So this will give us V naught divided by 1. Total minus 200K over 20K. Okay. And now V naught be the same as negative 10 volts. Now we have to estimate the source current as IS, the current flowing through the source. Now, recall at this point, you recall that for an ideal op-amp, the differential input voltage, Vn, based on the assumptions and the derivations, is the same as 0. And also, Vn, the differential input voltage, is the same as V sub P minus V sub N, for which we have P in here, right? Good. And since V sub P is 0, because the reference voltage here is equal to 0 volt, and so this terminal is the same as 0, then we already know from this difference parameter here that V sub P minus V sub N is equal to 0, so that V sub P is equal to V sub N. And now V sub P is 0. So since this is 0, so it means V sub N is equal to 0 as well. So hence, by Ohm's law, we have that I sub S, the source current, is the same as V sub S minus V sub N divided by R1. And we already know that V sub N is the same as 0, right? So V sub S is 1 divided by 20K. And that will give us 0.00005. So I sub S is the same as 0.05 milliamp. Then we have the output current. Now, by applying KCL at the output, so here we have that I naught is flowing out, and IF and IL are flowing in. So we have to compute I naught by KCL at the output. We have I naught is the same as I sub S plus I sub L. Okay, and we already know that I sub S is the same as 0.05 milliamperes. And I sub S is the same as I sub F because the current that flows in through this node, the entire current flows all the way. Okay, so there's no other branch that will divide the current. So therefore, you also observe that I sub L is the current through the load resistor. And by passive sign convention, you see it's flowing from negative to positive, such that I sub L will be the same as negative V naught divided by RL, right? So which is the same as negative minus 10 because we already have our V naught to be negative 10 volts divided by 20K. RL, which is 10K. This will give us 0.001, which is the same as 1 milliampere. So therefore, I naught is I sub S plus I sub L. We already know I sub S. Now we know I sub L. So I naught will be the same as 0.001 plus 0.00005. And this is going to give us 1.05 milliampere I naught. Okay, now that we've considered that, let us quickly look through the non-inverting configuration. Now, let's just get it here, non-inverting op-amp. Okay, and this op-amp produces an output signal that is in phase with the input signal. So it is not out of phase. There is no phase shift. And so let us consider an ideal circuit configuration for the non-inverting case. Okay, here's a perfect example. And you observe that the voltage source and its equivalent resistance are connected to the non-inverting terminal. Okay? And now, to designate the parameters accurately, it will be necessary to recall the assumptions for the ideal op-amp. Okay, so let us begin. the assumptions. Okay, let's wipe this. Love to wipe this. Probably replace it. So open, right? So let us recall the assumptions. Okay, so let's recall the assumptions for an ideal op-amp. Okay, so the first point to recall here is that the input resistance is infinite. So that is, we have an open circuit. If that is true, then it means that the current flowing through the inverting terminal will be 0, as already deduced, and the current flowing through the non-inverting terminal will be 0. And we can address this as the input current constraint, okay? Input current constraint. And secondly, we have that the output resistance is the same as 0, which shows a short circuit. Also, AV in is the same as V naught, and V in is the same as V naught over A, since the gain, the open loop gain, is infinitely large, so V in is also 0. And now, since V in is equal to 0, which is equal to V sub P minus V sub N, then V sub P is the same as V sub N. Then we can equally designate this as the input voltage constraint. So we have the input current constraint. IN is the same as I sub P, is the same as 0, and V sub P is the same as V sub N, is the input voltage constraint. So let us come back to the circuit. Now we have this as the reference voltage, which is 0 volts. This is the reference voltage. This is 0 volts. Okay, 0 volts. And this is also the reference voltage, which is 0 volts. Now, this is V sub N, and this is V sub P. So this is the non-inverting terminal, this is the inverting terminal. Now, we have that the current flowing through this, which is I sub N, is 0, right? 0, the input current constraint. And also, I sub P is equal to 0. So if I sub P is equal to 0, so it means that the current flowing through this terminal, I sub P, is equal to 0. So no voltage drop across R sub S. So the entire voltage, the source voltage, will be the same as the node voltage, since no voltage drop, because no current is flowing through the source resistance. Okay, and as such, no voltage drop across the source resistance, such that the entire source voltage will be the same as the node voltage. So V sub P will be the same as V sub S. And recall for the input voltage constraint that V sub P is the same as V sub N. So hence V sub N is also the same as V sub S as the source voltage, right? Okay, wipe this. Okay. So if this is clear, we have that the current flowing through this resistor is I sub 1, and the current flowing through this is I sub F. Okay. Then the current flowing this way is I sub F. So if we write KCL at the input, at this axis, at the input, okay? So it means that this is a node, right? So current I sub 1 flows in, I sub N, which is equal to 0, flows out, and I sub F flows out. So if we write KCL at the input, then we have I sub 1 flows into the node is the same as I sub N, which flows out, plus I sub F. Okay, and now this node here is 0 relative to the reference. So this is 0 volts. Okay, and at this point we have V naught, right? Okay, at the output. So by Ohm's law, I sub 1 will be 0 minus V sub N, which is the same as V sub S. Okay, so that will be 0 minus V sub N, and we already know that V sub P is the same as V sub S, and V sub P is the same as V sub N, so that V sub N therefore is the same as V sub S. So 0 minus V sub S divided by R1 will be the same as I sub N, which is equal to 0, the input current constraint. So that'll be 0 plus I sub F, which is V sub S, which is the same as V sub N, minus V naught divided by R. Perfect. So we now have that minus V sub S divided by R1 is the same as V sub S minus V naught divided by R sub F. So if we cross multiply here, that's minus V sub S, R sub F is R sub 1, V sub S minus V sub naught. So we have minus V sub S, R sub F, R sub 1, V sub S minus V naught, R1, right? So, okay. So, R1, V naught, R1 will be the same as V sub S this way, V sub S R1 plus V sub S RF. This is V sub S R1 plus RF, V naught R1, right? So V naught, the output voltage divided by, or the ratio of the output voltage to the source voltage, will therefore be the same as R1 plus RF divided by R1. Now this is the same as the closed loop voltage gain for the non-inverting amplifier. Good. So with this, we should be able to consider an example. Okay. So let's assume R1 is the same as 10 kilo ohms. RF is the same as 50 kilo ohms. RL, let's say RL let's take it out. So RL is let's say 10K. So this plus minus V naught here. And let's assume R sub S is the same as 20K. And V sub S, let's give it 1 volt. Okay. Then what do we want to evaluate here? Okay, let's try to evaluate V naught, I sub 1, I sub L, the open loop gain. Then let's also evaluate V in when this closed loop gain, when the open loop gain is the same as 100,000. And I sub S when the input resistance is 1 mega ohms. Now, so if we take the first point, we already know that let's write this. Okay, we already know that the closed loop gain is the same as the ratio of the output voltage to the source voltage for the non-inverting op-amp, which is the same as 1 plus RF over R1. Okay. Now the output voltage follows directly from here to make V naught the subject formula here. 1 plus RF divided by R1 V sub S. Now this will be the same as 1 plus RF is 50K divided by 10K times 1. So this will truncate this, that's 5 plus 1, which is equal to 6 volts. So V naught is equal to 6 volts. Now, the second point here is I sub 1. Now, recall that V sub in, the input voltage, is 0. And V sub S must be developed across R1, right? That's V sub S. This is V sub S. This is V sub S, right? Okay. So if that's what it is, by Ohm's law, we have that I1 the same as Vref minus Vs divided by R1. And now this will give us 0 minus minus, that's plus. That will give us V sub S divided by R1 which is 1 over 10k, which is the same as 0.1 million. Okay. So it means that a sub 1 is the same as 0.1 million. Now the next point here is I sub L. Now by Ohm's law, I sub L, this is V naught here, with respect to the reference voltage. So I sub L will be V naught minus Vref, V naught minus Vref divided by RL. And then let's cross this. This should be the same as V naught because Vref is 0 divided by RL. We already know V naught to be 6 volts, which is 6 divided by 10k. So RL is the same as 0.6 milliamps. Then the next point, we've taken care of this, this, and this. So the closed loop gain is the same as V naught divided by V sub S. And we know V sub S to be 1 and V naught is 6. So that's 6 divided by 1, which is equal to 6. So closed loop gain is the same as 6. Now the for us to estimate V in, recall that V naught is the same as A V in, right? Such that V in is the same as V naught divided by A. Now we already have the open loop gain to be 100,000, so that will be 6 divided by 100,000. So V naught in this case will be 60 microvolts root mean squared. Okay. And then the last point here is I sub S, which is the same as V in divided by the input resistance. And the input resistance is given as 1 mega ohms. So we have V in already. This is V in. This is V in. V in. So V in is 60 microvolts root mean squared divided by 1 mega ohm. So IS is the same as 60 picofarad. Okay, I think that's for that. I need to be good to mention at this point one beautiful example of the non-inverting op-amp, which is a unity gain version of the ideal non-inverting op-amp. So we'll just talk about that and then call it a day. So here we have this minus, so the feedback goes back into this, and then this is positive, negative, so that's negative, V naught. Okay. Now the feedback resistance is the same as 0. So this is referred to as the unity gain version of the ideal non-inverting op-amp. Now, from this configuration, you will recall that the closed loop gain is the same as V naught over V sub S, which is the same as 1 plus R sub F divided by R sub F. Now, if the feedback resistance is 0 and this reduces to 0, then the closed loop gain is the same as V naught V sub S equal to 1, which makes it the unity gain amplifier. And this, therefore, implies a unity gain buffer amplifier. So from this analysis, so it means that V naught is the same as V sub S, which implies that the input voltage follows the output. So should we desire a system where the output voltage will be the same as the input voltage, then the unity gain buffer amplifier will be a perfect fit for that circuit. And hence, the unity gain buffer amplifier is also referred to as the voltage follower. Voltage follower. Largely because the input voltage follows the output voltage. Now, it is actually called a buffer because a buffer is meant for storage, right? So it means that we are not losing any of the part of the energy is not dissipated. That's what it means. No dissipation. So if we have 2 volts input as the input source, then as a source input, then the output will also be 2 volts. So it is therefore called a source, a buffer rather, which is a storage buffer, because when used to interconnect the source and the load, the voltage seen at the source will be the same as the voltage seen at the load. So if, for instance, we try to connect this, okay. So let's assume we have this, and then we have a resistor here connected to this. Let's say this is 4 volts. So the V sub S is equal to 4 volts here. And then we have our load. This is equal to 10 ohms. So here we have VL. So this is positive, negative. F is 0. Okay. Then let's assume this R1 and then it's the same as 5 ohms. So let's observe what will happen here. Now, if you observe the circuit, so well, and then recall the assumptions, you recall that I sub P is equal to 0 and I sub N is equal to 0, the input current constraint. Now, if I sub P is equal to 0, so it means the current flowing through the 5 ohm resistor, I sub P is equal to 0. So no voltage drop here. Okay? So in other words, V5 is the same as I sub P R1, which is 0 times 5, which is 0 volts. So it means that the entire source voltage will appear at this node. So at this node, we are going to be having at VP is going to be 4 volts, entire 4 volts. Okay? So in other words, the entire 4 volts at the source is same at this node, since there's no voltage drop across this resistor, likely because the current flowing through this terminal is 0. Beautiful. And also recall the voltage constraint that Vp is the same as Vn. So at this point, Vn is also equal to 4 volts. So if 4 volts is same here and Vn is 4 volts, then at this node, we're also going to have 4 volts. Hence, the voltage across the 10 ohm resistor will be the same as 4 volts. So you see, likely because we use the voltage follower, or better still, the unity gain buffer, we were able to present the same voltage at the load as we have, produced by the source. So hence the voltage follower or the unity gain buffer amplifiers, or amplifier rather, may be used in digital circuit design. Well, I think this is a good place to stop, and we'll pick things up from here in our next class. Do have a great day, and bye for now.